There is a place in the constellation Sagittarius, roughly 390 light-years from Earth, that astronomers call Sagittarius B2. It is a giant molecular cloud, a vast, cold region of gas and dust hovering near the center of the Milky Way, one of the most chemically complex regions of the galaxy ever studied. And what they have found inside it, cataloged over decades of radiospectroscopy, includes ethyl formate, a molecule responsible for the flavor of raspberries. It includes acetic acid. It includes propyl cyanide. It includes glycolaldehyde, a simple sugar. And it includes ethanol, drinkable ethyl alcohol, in quantities estimated at roughly 460 quintillion liters, spread across the vast diffuse cloud. None of this is accessible. None of it is concentrated into anything you could bottle or taste. It is dispersed across light-years of space at densities far thinner than any laboratory vacuum. But the chemistry is real. The same molecular building blocks that go into food, into fermentation, into biological metabolism, they exist, fully formed, in the cold dark between the stars, assembled by cosmic radiation acting on ice-coated dust grains over millions of years without any biology to drive the process. The universe does not need life to make the molecules of life. It makes them anyway, everywhere. That fact is not a curiosity. It is a clue. It tells us that the ingredients of biology are not a fluke of Earth. They are a product of basic chemistry in the interstellar medium, distributed throughout every star-forming region in every galaxy, arriving at newly forming planets through the comets and asteroids that sweep through early solar systems. The question of why life exists on Earth is complicated. The question of why life's raw materials exist on Earth has a simple answer. Because they are everywhere. The Milky Way, the galaxy we live inside, is a structure that most people have seen in photographs, but almost no one has seen in its full context, because we are inside it. We cannot step outside and look back. Everything we know about the large-scale structure of our own galaxy, its spiral arms, its central bar, the dimensions of its disk and halo, has been pieced together from observations made inside it, the way you might try to map a city by walking its streets without ever climbing to a high enough point to see the whole layout at once. The Milky Way is a barred spiral galaxy. At its center sits not just Sagittarius A star but a bar of stars, an elongated, roughly rectangular structure of densely packed older stars that extends outward from the nucleus, flanked by the beginnings of the spiral arms. The bar is about 27,000 light-years long. The spiral arms, we currently distinguish four major ones, named Norma, Scutum Centaurus, Perseus, and Sagittarius, are not rigid physical structures but density waves, regions of the disk where gas and dust pile up as the wave passes through, triggering bursts of star formation and giving the arms their bright blue-white appearance. The arms rotate more slowly than the individual stars, which pass through them over time the way cars on a highway pass through a patch of slow traffic. Our sun passes through a spiral arm roughly once every 100 million years. The solar system is currently situated in a minor spur between the Sagittarius and Perseus arms called the Orion Spur or Orion Arm, about 26,000 light-years from the galactic center. We orbit the center of the Milky Way at a speed of about 220 kilometers per second, completing one full orbit roughly every 225 to 250 million years, a unit of time sometimes called a galactic year. In the time since the solar system formed, it has completed about 18 to 20 galactic orbits. The last time Earth was in roughly this same position relative to the galaxy, the Triassic period was just beginning. The first dinosaurs were emerging, and the supercontinent Pangaea was beginning its slow breakup. The galactic year puts geological time into a different kind of perspective. The disk of the Milky Way is not flat. It is warped, bent upward on one side and downward on the other relative to the average plane of the disk, like a vinyl record left in a warm room. The warp was confirmed in precise detail in 2019 using a sample of Cepheid variable stars mapped by the Warsaw Observatory's OGLE survey. The cause of the warp is thought to be the gravitational influence of the Magellanic Clouds pulling on the outer disk as they orbit. The outer disk is also not sharply bounded. It frays into a complex of stars, streams, and stellar overdensities that extend far beyond the canonical boundary of the visible disk and the full extent of the Milky Way's stellar halo. The diffuse spherical distribution of old, metal-poor stars and globular clusters surrounding the disk reaches outward hundreds of thousands of light-years. The total mass of the Milky Way, including dark matter, is estimated at somewhere between 500 billion and 1.5 trillion solar masses, with the wide range reflecting the difficulty of measuring the mass of an extended dark matter halo you cannot directly see. The epoch of reionization is one of the least observed and most consequential periods in the history of the universe. After the Big Bang, after the cosmic microwave background was released, the universe entered what is called the cosmic dark ages, a period lasting hundreds of millions of years during which no stars yet existed. The universe was filled with neutral hydrogen gas, and there was no source of light. Then the first stars and galaxies ignited. Their ultraviolet radiation began to ionize the surrounding neutral hydrogen, creating bubbles of ionized gas that slowly expanded, merged, and eventually, by about 1 billion years after the Big Bang, had reionized essentially all the hydrogen in the intergalactic medium. This transition from a universe of neutral light-absorbing gas to a universe of transparent ionized plasma was not instantaneous. It was a process that unfolded over hundreds of millions of years, driven by the radiation from the first galaxies and quasars. The James Webb Space Telescope is observing galaxies from this epoch with unprecedented clarity, studying the sources of ionizing radiation that drove reionization and tracking how the early universe became transparent. In 2022, Webb detected galaxies from just a few 100 million years after the Big Bang with surprising brightness and structure, more developed than models predicted, suggesting that star formation in galaxies centered in the early universe were more efficient than expected. This would help transformers in the universe as the phenomenon of Big Bang appears to isolation has seen in the first 300 million. The universe was a hot, dense plasma in which photons and baryons, ordinary matter, were tightly coupled. Sound waves propagated through this plasma, compressing and rarefying the gas, carrying energy outward at a speed roughly 60% the speed of light. When the universe cooled enough for neutral atoms to form, the moment of recombination, when the CMB was released, the sound waves froze in place. The distance those waves had traveled from their origin became imprinted in the distribution of matter as a preferred clustering scale, a faint excess of galaxies separated by about 500 light-years at the time of recombination, which has expanded with the universe to about 500 million light-years today. This scale is measurable in the large-scale distribution of galaxies, and it serves as a standard ruler in the universe, a known physical scale that can be used to measure cosmic distances and the expansion rate. The Baryon Acoustic Oscillation Scale has been measured in surveys encompassing millions of galaxies, and the results are in tension, though not precisely the same tension, with local distance measurements. The universe is trying to tell us something. We are still working out what. The bullet cluster is perhaps the most visually compelling single piece of evidence for dark matter's existence and nature. It consists of two galaxy clusters that have passed through each other at roughly 35 million kilometers per hour, the aftermath of a collision between two of the largest bound structures in the universe. When the clusters collided, the hot gas that makes up most of the ordinary matter in each cluster slammed together, slowed by electromagnetic interactions and heated to temperatures of hundreds of millions of degrees, glowing in X-rays. The galaxies themselves, being mostly empty space, passed through each other like two swarms of bees, barely interacting. And the dark matter, inferred through gravitational lensing of background galaxies, also passed through without interacting, but not with the gas. The dark matter halos moved with the galaxies, not with the gas. The result is a cluster where the ordinary matter, the hot gas, visible in X-rays, is offset from the gravitational center of mass, visible through lensing. The two mass components are separated. Dark matter does not interact with itself or with ordinary matter through the electromagnetic force, only through gravity. The bullet cluster makes this visible. It is the closest thing to a direct photograph of dark matter that exists. When you look at the night sky and pick out a bright star at random, there is about a 70% chance it is a red dwarf, a small, cool, dim star burning hydrogen so slowly it will last for tens to hundreds of trillions of years. Red dwarfs dominate the galaxy by number. They are the most common type of star by a wide margin, and yet because they are so dim, not a single red dwarf is visible to the naked eye from Earth. Proxima Centauri, the closest star to our Sun at just over 4 light-years, is a red dwarf, and it shines at less than 1/10,000th the luminosity of our Sun, completely invisible without a telescope. The nearest naked-eye star in the Alpha Centauri system, what appears as a single bright star near the Southern Cross, is actually a binary of two Sun-like stars, Alpha Centauri A and Alpha Centauri B, orbiting each other closely, with Proxima orbiting the pair at great distance. The possibility of a mission to Alpha Centauri has moved from pure science fiction towards something that at least theoretically feasible timescale discussions can be had about. The fastest spacecraft ever launched, the Parker Solar Probe, reached speeds around 690,000 kilometers per hour at its closest approach to the Sun. Remarkable, but at that speed, the journey to Alpha Centauri would take about 6,000 years. The Breakthrough Starshot Initiative, announced in 2016 by Stephen Hawking and Yuri Milner, proposed a different approach, using powerful Earth-based lasers to accelerate gram-scale light sails, postage stamp-sized spacecraft, to about 20% the speed of light, reaching Alpha Centauri in about 20 years. The engineering challenges are extraordinary. The laser array would need to deliver gigawatts of focused power to a tiny sail moving at hypersonic speeds. The sail material must withstand the heating and radiation pressure of the laser beam without being destroyed. The spacecraft must carry instruments capable of gathering and transmitting meaningful scientific data while weighing almost nothing. And the data transmission from 4 light-years away from a gram-scale transmitter is a profound challenge. None of these problems are solved, but none of them are obviously impossible. Whether Starshot or something like it ever launches in any form is a question for the century ahead. Proxima Centauri has its own planet, Proxima b, discovered in 2016 using the radial velocity method. It is at least 1.5 Earth masses and orbits within the habitable zone of Proxima Centauri. It is also tidally locked. One hemisphere permanently faces the star, one permanently faces away, and Proxima Centauri is an active flare star that regularly blasts its planets with ultraviolet and X-ray radiation at intensities that would strip the atmosphere of an unprotected world. Whether Proxima b has an atmosphere, and whether any atmosphere it has can survive the radiation environment is unknown. In 2022, a second candidate planet, Proxima d, was identified, even closer to the star, likely less than a quarter of Earth's mass. If confirmed, it would be one of the lightest exoplanets ever detected. The nearest stellar system to Earth may host multiple planets. We simply do not yet know what they are like. The transit of Venus. When Venus passes directly in front of the Sun as seen from Earth, was for centuries one of the most important astronomical events conceivable, because timing the transit from different locations on Earth could be used to calculate the distance from Earth to the Sun through parallax, a measurement that would then calibrate the distances to all other solar system bodies. Transits of Venus come in pairs separated by 8 years, with each pair separated by over a century. The transits of 1761 and 1769 were international scientific expeditions of extraordinary scope. Astronomers from Britain, France, Russia, and other nations traveled to remote locations around the globe, including Tahiti, where James Cook commanded the HMS Endeavour and hosted Charles Green of the Royal Observatory in making the timing measurements that were the nominal scientific purpose of the voyage, before Cook opened sealed orders and sailed south in what became the first recorded European encounter with the eastern coast of Australia. The transit observations themselves were hampered by what became known as the black drop effect, an apparent visual connection between the disk of Venus and the edge of the Sun, just as Venus's disk appeared to touch the solar limb, blurring the contact timing and reducing the precision of the distance measurements. The black drop effect was eventually understood to be caused by Venus's thick atmosphere combined with the non-uniform brightness of the Sun's limb. But in 1761, it frustrated the astronomers who had sailed halfway around the world to make the observation. The resulting estimate of the Earth-Sun distance was approximately 153 million kilometers, remarkably close to the modern accepted value of about 149.5 million kilometers. The transits of Venus in 2004 and 2012 were the most recent pair. The next transit of Venus will not occur until December 10 and 11 of 2017. The question of what a Thorne-Zeitkow object is rarely comes up in popular space discussions, but it should, because it represents one of the strangest predicted outcomes of stellar evolution. A Thorne-Zeitkow object, named for Kip Thorne and Anna Zeitkow, who proposed them theoretically in 1975, is a star with a neutron star hidden inside it. The scenario arises in binary star systems where one star has already undergone a supernova and become a neutron star, and subsequently, through orbital evolution, the neutron star spirals inward into the envelope of its companion, a giant star, and sinks to the center. The result is a star that looks superficially like a large, cool, red supergiant, but has a neutron star as its core rather than a normal stellar interior. The neutron star provides a heat source and disrupts the normal nuclear burning structure, producing a distinctive chemical abundance pattern in the giant's outer layers, particularly unusual enrichments of certain heavy elements like molybdenum, lithium, and rubidium that are produced in the unusual nuclear burning environment around the neutron star surface. In 2014, a strong candidate for an actual Thorne-Zeitkow object, designated HV 21112, was identified in the Small Magellanic Cloud, though subsequent analysis has been ambiguous and debate continues. If Thorne-Zeitkow objects exist as predicted, they represent an entire category of stars hiding something extraordinary at their hearts, stars that are not what they appear to be. The Gemini program, which bridged the gap between the single-person Mercury capsules and the three-person Apollo spacecraft, is one of the most technically productive and least remembered chapters of the space race. Between 1965 and 1966, 10 crewed Gemini missions flew, and every major technique required for the Apollo moon mission was demonstrated for the first time during Gemini. Spacewalking, extravehicular activity, was demonstrated imperfectly at first. Ed White became the first American to walk in space during Gemini 4 in June 1965, spending about 23 minutes outside the capsule tethered to it, maneuvering with a handheld gas gun. He described it as the most comfortable and enjoyable experience of his life, and had to be ordered back inside by flight controllers. Later Gemini spacewalks proved far more difficult. Astronauts found that working in a pressurized spacesuit in the vacuum was exhausting, with no surfaces to push against, every motion producing an equal and opposite reaction that sent the suited body tumbling. Gene Cernan, during Gemini 9A, was so exhausted by his spacewalk that his helmet faceplate fogged from sweat, partially blinding him, and he nearly could not get back inside. Orbital rendezvous, bringing two spacecraft together in orbit, was achieved for the first time during Gemini 6A and Gemini 7 in December 1965, when Frank Borman and Jim Lovell, who had spent 2 weeks in orbit aboard Gemini 7 to test the effects of long-duration spaceflight, watched Wally Schirra and Tom Stafford in Gemini 6A pull alongside them to within about 30 centimeters, close enough to read each other's name patches through the windows, without physically docking. Actually joining two spacecraft in orbit was achieved for the first time during Gemini 8 in March 1966, when Neil Armstrong and Dave Scott docked with an unmanned Agena target vehicle. Shortly afterward, a thruster on the Gemini capsule stuck open and began spinning the joined spacecraft at an increasing rate. Armstrong undocked from the Agena, which turned out to make things worse, as the Gemini thruster was now spinning the capsule alone at a rate approaching 1 revolution per second, the fastest spin ever experienced by a crewed spacecraft. Armstrong used the re-entry thrusters, violating mission rules by activating them before re-entry, to stop the spin and save the crew. The mission was aborted. Armstrong was described by those who reviewed the incident as having demonstrated extraordinary skill under pressure, and the decision likely saved his life and Scott's. 2.5 years later, Armstrong would land on the moon. The Soviet Luna program achieved a series of remarkable firsts throughout the 1960s and 1970s that are rarely given the attention they deserve in Western histories. Luna 9, in February 1966, became the first spacecraft to make a soft landing on the moon, 3 months before the American Surveyor 1 achieved the same. Its photographs of the lunar surface at close range were among the first ever taken from the moon's surface, and they were immediately significant for one specific reason. Before Luna 9 landed, there was genuine scientific debate about whether the lunar surface was covered in a deep layer of loose dust, fine enough that any landing spacecraft, or future astronauts might simply sink into it. Luna 9's images showed a rocky, relatively firm surface. The moon was not quicksand. Luna 16 in 1970 became the first robotic mission to collect samples from another world and return them to Earth, predating the Apollo 12 samples by only months in timeline, but representing a completely different approach. Fully automated, no crew, no risk of human life. Luna 17, also in 1970, delivered Luna Code 1, the first robotic rover to operate on the surface of another world, which drove across the lunar surface for 10 months, covering about 10 kilometers and returning thousands of photographs. Luna Code 2, delivered in 1973, covered nearly 40 kilometers. No subsequent lunar rover would exceed this distance until China's Yutu-2 rover, which began operating on the far side of the moon in January 2019, the first mission ever to land on the lunar far side, a hemisphere permanently facing away from Earth, where no direct communication with Earth is possible, and where a relay satellite in a halo orbit around the second Earth-Moon Lagrange point is required to maintain contact. China's space program has matured into the most rapidly developing major space program in the world. The Tianwen-1 mission delivered a rover named Zhurong to the surface of Mars in May 2021, making China only the second nation to successfully operate a rover on Mars. The Tiangong space station, China's own modular orbital outpost, has been continuously inhabited since June 2021, making China only the third entity after the US and Russia to maintain a continuous human presence in space, and the only one to do so independently. China has stated its intention to land astronauts on the Moon before 2030, and its Chang'e series of lunar missions has returned samples from the Moon's surface twice. Chang'e 5 in December 2020 brought back about 1.5 kilograms of lunar material from a location called Mons-Rumker, a region that had never been sampled before and whose samples turned out to be about 2 billion years younger than any previously returned lunar samples, suggesting volcanic activity on the Moon far more recently than previously thought. Chang'e 6 in mid-2024 returned samples from the South Pole Aitken Basin on the lunar far side, the oldest and largest impact crater in the solar system, for the first time in history. What those samples reveal about the composition and geological history of the far side may reshape our models of the Moon's formation and evolution. Japan's Hayabusa missions represent an entirely different kind of solar system sample return, targeting not the Moon but asteroids. The original Hayabusa spacecraft reached the asteroid Itokawa in 2005, a peanut-shaped rubble pile about 540 meters long, held together only by weak gravity and the interlocking of its own component fragments, and made 2 brief touchdowns to collect samples, fighting through system failures that should have ended the mission but did not, returning to Earth in 2010. The sample capsule landed in the Australian outback. Inside were a few thousand tiny particles, micron-scale grains, of material from Itokawa. They were of S-type asteroid composition, consistent with the most common class of meteorites that fall to Earth, confirming the connection between asteroid types and meteorite families. Hayabusa 2 reached asteroid Ryugu in 2018, a spinning top-shaped C-type asteroid about 900 meters across, delivered a small rover and a lander, and then, in one of the most audacious moments in robotic space exploration, fired a copper impactor into Ryugu's surface at 2 kilometers per second, creating an artificial crater, and then flew down into the fresh crater to collect subsurface material that had not been weathered by space radiation. The sample capsule returned to Earth in December 2020. Analysis of the Ryugu samples has revealed amino acids, 23 distinct amino acids, in a pristine sample of carbonaceous asteroid material, providing the clearest evidence yet that the building blocks of proteins can form in space and be delivered to planetary surfaces by impacts. NASA's OSIRIS-REx mission did the same at the asteroid Bennu, a diamond-shaped carbonaceous near-Earth asteroid, about 500 meters across, and returned its sample capsule to Earth in September 2023. The Bennu sample, about 250 grams, contained carbon-rich material and water-bearing clay minerals, consistent with a body that formed in the early solar system from material that had been in contact with liquid water. The samples from Ryugu and Bennu together represent the most pristine carbonaceous asteroid material ever analyzed in Earth laboratories, and scientists expect to be working through their implications for decades. These asteroids are remnants from the very earliest solid material in the solar system, the planetesimals from which the planets ultimately assembled, and they carry a chemical record of the conditions in the protoplanetary disk before any planet had formed. The story of how the terrestrial planets formed from such primitive material involves a phase of spectacular violence. The protoplanetary disk that surrounded the early Sun was initially a diffuse disk of gas and dust, but within the first few million years, solids began to clump, first through electrostatic and van der Waals forces between dust grains, then through low-velocity collisions that caused grains to stick and grow into centimeter and meter-scale bodies, then through a process called streaming instability, where concentrations of pebble-sized particles become dense enough to gravitationally collapse directly into kilometer-scale planetesimals. From there, gravitational runaway accretion took over. Larger bodies swept up smaller ones, growing into planetary embryos and eventually the terrestrial planets we know, over a period of about 100 million years. The final stage of this assembly involved giant impacts, collisions between planetary-scale bodies that were energetic enough to melt the silicate mantles of both impactors and release enormous amounts of material into orbit. The Moon almost certainly formed from exactly such an event. A Mars-sized body called Theia collided with the proto-Earth at a glancing angle about 4.5 billion years ago. The iron cores of both bodies merged into what became Earth's core. The silicate material, vaporized and melted, was thrown into orbit and within decades to centuries reassembled into the Moon. The Moon's composition, similar to Earth's mantle, depleted in volatile elements with a small iron core, is consistent with this giant impact hypothesis, and the theory has been refined in recent years to accommodate newer isotopic measurements that require the impactor and target to have been nearly identical in composition, possibly because they formed at similar distances from the Sun. Earth's moon is in many ways a world that rewards deeper examination beyond its obvious face. The lunar surface is not simply cratered rock. It is divided into two fundamentally different types of terrain. The bright, heavily cratered highlands, the anorthosites, are the ancient original crust of the Moon, floating up from the lunar magma ocean that covered the entire body in its first 100 million years as lighter minerals crystallized and rose to the surface. The dark, relatively smooth regions, the Maria, Latin for seas, are vast ancient lava flows that filled impact basins over the following billion years, as heat from the decay of radioactive elements in the lunar interior drove episodic volcanism. The distribution of Maria is heavily skewed toward the near side of the Moon, the side that always faces Earth. The far side is almost entirely highlands with very few Maria. The reason for this asymmetry is not fully understood. One hypothesis involves a slow, asymmetric crystallization of the lunar magma ocean driven by the tidal heating effect of the nearby Earth. Another involves a giant impact on the far side that thickened the crust there, making it harder for volcanic magma to breach through. Neither explanation is fully satisfying. The Moon's asymmetry is a genuine unsolved problem. The craters of the Moon preserve a record of impact bombardment stretching back more than 4 billion years. The oldest craters are enormous, multi-ring basins like the South Pole Aitken Basin, about 2,500 kilometers across and 13 kilometers deep, the largest and deepest impact crater in the solar system. These ancient basins record the period of the late heavy bombardment, a proposed spike in impact rates occurring about 3.9 billion years ago, roughly coinciding with a period of dynamical instability in the outer solar system when Jupiter and Saturn migrated through resonance with each other, destabilizing the Kuiper belt and asteroid belt, and sending a swarm of objects into the inner solar system. Evidence for the late heavy bombardment comes primarily from the ages of lunar rocks returned by Apollo, many of which cluster around 3.9 billion years in their impact reset radiometric ages, but whether this represents a true spike in impacts or simply the tail end of a longer declining impact rate is actively debated. Whatever the truth, life on early Earth was forming or attempting to form in the middle of this bombardment. Either it survived the impactors, or it was repeatedly destroyed and had to start over, or it found refugia deep in the ocean or underground where the surface catastrophes did not penetrate. The Mariner program, NASA's first robotic exploration of the inner planets and Mars, produced discoveries that stunned the scientific community and the public alike in the 1960s and early 1970s. Mariner 2 in 1962 became the first spacecraft to fly past another planet, Venus, and confirmed that Venus is extremely hot, ruling out the science fiction speculation about a tropical jungle Venus beneath its clouds. Mariner 4, in 1965, returned the first close-up photographs of Mars, and they showed a cratered, moon-like surface, killing the popular image of Mars as a living world and deeply disappointing those who had hoped to find cities, canals, or any visible evidence of life. The canals of Mars, reported by 19th-century astronomers like Percival Lowell, who had dedicated his observatory and much of his career to mapping them, were not visible. They had been an optical illusion, the human visual system creating pattern from ambiguous detail. Mariner 9, in 1972, became the first spacecraft to orbit another planet and, arriving during a planet-wide dust storm that initially obscured the surface entirely, waited out the storm and then revealed as the dust cleared the first views of Olympus Mons, Valles Marineris, and the dried-up riverbeds that proved Mars had once had flowing water. The Mars that Mariner 9 revealed was a world that had once been warmer and wetter, a world with a history. Viking 1 and Viking 2 landed on Mars in 1976 and remain the only American spacecraft to date to have conducted biology experiments directly on the Martian surface. The biology package included 4 experiments, each designed to detect signs of metabolic activity in Martian soil. 3 of the 4 experiments gave positive results on initial testing, results that, if produced by a soil sample from Earth, would immediately be interpreted as evidence of microbial metabolism. But the 4th experiment, the gas chromatograph mass spectrometer, which searched for organic molecules, found nothing. Essentially no organic carbon in the Martian surface soil. Without organic molecules, the positive results of the biology experiments were attributed to chemical rather than biological activity. The Martian soil contains perchlorates and other highly reactive chemicals that mimic the signals of metabolism without being biology. This interpretation has never been fully settled. Some researchers have continued to argue that the Viking biology results are consistent with life, and that the organic molecule experiment had limitations that might explain its null result. The question of what Viking actually detected in 1976 is one of the longest-running debates in the history of planetary science. It remains officially open. The concept of stellar populations extends beyond the population I and population II division that most astronomy texts discuss. Population 3 stars, the hypothetical first generation of stars, forming from the nearly pure hydrogen and helium of the Big Bang, would have had extraordinarily different properties from any star observable today. Without heavy elements to facilitate the fragmentation of collapsing gas clouds, the first stars may have been supermassive, hundreds or even thousands of times the mass of our Sun, burning intensely for only a few 100,000 years before exploding in supernovae or collapsing directly to black holes. A star of several hundred solar masses would be so luminous that it would be in danger of blowing itself apart through radiation pressure alone, approaching or exceeding what is called the Eddington luminosity, the theoretical maximum luminosity at which radiation pressure equals gravity. Population 3 stars would have been the first sources of elements heavier than helium in the universe, the first to seed the intergalactic medium with carbon, oxygen, nitrogen, iron, the periodic table's inventory beyond the lightest elements. Their deaths would have been among the most energetic events in the universe's history, and they would have been the primary sources of the ionizing radiation that drove cosmic reionization. We have never directly observed a population 3 star. They all died billions of years ago, but their influence is detectable in the composition of the most ancient surviving population 2 stars, which carry the chemical fingerprints of the population 3 ejecta they formed from. And JWST, peering into the epoch of reionization, may eventually detect the light of young galaxies whose spectra are consistent with population 3 stellar populations, young enough in the early universe that later generations of enriched stars had not yet had time to dominate. In 2023, a candidate individual population 3 star was identified through JWST observations, gravitationally lensed to extraordinary brightness by a foreground galaxy cluster, at a redshift corresponding to the universe being less than 1 billion years old. The candidate spectrum was consistent with a star of essentially zero metallicity. If confirmed, it would be the first direct observation of the first generation of stars. The result is preliminary, but it demonstrates what JWST makes possible. Pulsars are not uniform in their properties, and the variety of pulsar types that have been cataloged over the decades of radio astronomy tells a rich story about the range of neutron star physics. Some pulsars slow down regularly and predictably, losing rotational energy through magnetic braking as their electromagnetic radiation carries angular momentum away, and their spin-down rates can be used to calculate the age of the pulsar and the strength of its magnetic field. Others experience what are called glitches, sudden, spontaneous speed-ups in rotation, where the pulsar spins up by a tiny amount and then gradually slows back to the expected trend. Glitches are thought to be caused by the sudden transfer of angular momentum from the superfluid interior of the neutron star, where neutrons flow without viscosity, to the solid outer crust. The crust spins slightly slower than the superfluid, building up a stress, and then they suddenly couple, spinning the crust up. Studying glitches gives physicists a window into the interior structure of neutron stars, the deepest and densest matter accessible to observation anywhere in the universe, where the pressure is so extreme that the behavior of matter is governed by quantum chromodynamics in ways that cannot currently be solved analytically. The double pulsar system, designated PSR J0737339, discovered in 2003, is one of the most remarkable objects in the observational toolkit of physics. It is a binary system in which both objects are just over 2 hours to gravitational wave emission. The two pulsars are spiraling toward each other at a rate that matches the predictions of general relativity to an accuracy of better than 1 part in 10,000. They will merge in roughly 85 million years, producing a burst of gravitational waves that would be detectable across the entire observable universe. The double pulsar has been used to test effects including the Shapiro delay, the slowing of light as it passes through a gravitational field, gravitational redshift, and the rate of periastron advance, all with precision that exceeds any other laboratory for testing Einstein's theory. It is arguably the best clock in the universe for relativistic physics, and every observation refines the picture of how gravity behaves in the most extreme conditions outside a black hole. The first exoplanet confirmed around a main sequence star, 51 Pegasi b, discovered in 1995 by Michael Mayer and Didier Queloz using the radial velocity method, for which they shared the Nobel Prize in Physics in 2019, was so surprising that some astronomers initially refused to believe it. 51 Pegasi b is a gas giant roughly half the mass of Jupiter, orbiting its star at just over 7 million kilometers, about 1/20th the distance from Earth to the Sun. Its orbital period is 4¼ days. Before this discovery, planetary formation theory predicted that gas giants could only form far from their stars, in the cold outer regions of the protoplanetary disk where ices could contribute to planetary cores massive enough to attract the enormous gas envelopes that define a gas giant. A Jupiter-sized planet at Mercury-like distances was not supposed to exist. Its existence demanded that the planet had formed far out and migrated inward, a process now understood to be common, driven by gravitational interactions between the young planet and the disk of gas it is still embedded in during the early stages of its formation. Planetary migration has subsequently been invoked to explain the architecture of many exoplanet systems, including, possibly, our own, Jupiter's hypothesized early inward migration and subsequent outward retreat shaping the inner solar system. The planet HD 18973b is one of the most studied hot Jupiters in the sky, and what its atmosphere contains is a reminder that the universe's inventory of weather is far beyond anything Earth can produce. HD 18973b has an atmosphere where the temperature on the dayside exceeds 1,000 degrees Celsius. Winds blow from the dayside to the nightside at speeds exceeding 8,000 kilometers per hour, the fastest winds of any planet measured. And the clouds in its upper atmosphere are made of silicate particles, tiny grains of glass, that are lofted aloft by the intense thermal dynamics and precipitate outward as glass rain, blown sideways by winds moving faster than the fastest artillery shell. On this world, it rains glass, sideways, at supersonic speeds. The planet itself cannot be seen directly. It is detected through the transit method and through secondary eclipse measurements, and its atmosphere has been analyzed through transmission spectroscopy, where the light of the star filtered through the planet's atmosphere during transit carries the chemical fingerprints of whatever is in it. The transmission spectrum of HD 18973b shows the presence of sodium, water vapor, methane, and carbon dioxide, a rich chemistry driven by the extreme temperatures. The blue color of the planet, inferred from measurements of reflected starlight, comes from the scattering of light by those silicate cloud particles, the same process that makes Earth's sky blue but driven by glass rather than air molecules. The concept of atmospheric biosignatures, chemical signs of life detectable in a planet's atmosphere from light years away, is the scientific foundation of the search for life on exoplanets, and it is more complicated than it sounds. The most discussed biosignature is oxygen, specifically molecular oxygen or ozone, because oxygen is highly reactive and would quickly be removed from any planetary atmosphere by chemical processes if it were not being continuously produced by photosynthesis. An oxygen-rich atmosphere on an exoplanet would be strong evidence for oxygenic photosynthesis for a biosphere like Earth's. But oxygen can also be produced abiotically. Photolysis of water vapor by stellar ultraviolet radiation can produce oxygen without any biology, particularly around certain types of stars. Any claimed detection of atmospheric oxygen must be evaluated in context. The same is true of methane. Methane and oxygen together are a more compelling combination because in the presence of oxygen, methane should react away quickly, and the simultaneous presence of both requires an active production source for one or both. On Earth, both are produced biologically. Other proposed biosignatures include nitrous oxide, produced by denitrifying bacteria, and the so-called red edge, a sharp increase in reflectivity at near-infrared wavelengths caused by plant chlorophyll, which produces a distinctive spectral feature in Earth's reflected light that might be detectable in the reflected light of a nearby terrestrial exoplanet. JWST has taken the first steps toward atmospheric characterization of potentially habitable exoplanets, studying the TRAPPIST-1 system in detail. The results so far have been mixed. TRAPPIST-1b and TRAPPIST-1c appear to lack thick carbon dioxide atmospheres, which is either reassuring, suggesting they are not Venus-like, or concerning, suggesting they may have lost their atmospheres entirely under bombardment from the star's flares. The other TRAPPIST-1 planets, including TRAPPIST-1e and F in the habitable zone, require far more observing time to characterize because their signals are more subtle. The detection of a carbon dioxide-bearing atmosphere on a habitable zone planet would be a major milestone. The detection of oxygen combined with methane would likely be announced as one of the greatest scientific discoveries in human history. The relationship between mass extinction events and astronomical phenomena is an area of active research that challenges any comfortable sense that the solar system is a safe, stable neighborhood. We have discussed the Chicxulub impact and the proposed gamma-ray burst connection to the Ordovician extinction. The Permian-Triassic extinction, the largest in Earth's history, killing roughly 96% of marine species and 70% of terrestrial vertebrate species about 252 million years ago, has been linked primarily to the eruption of the Siberian Traps, one of the largest volcanic events in Earth's history, which over tens of thousands of years released enough carbon dioxide and sulfur dioxide to acidify the oceans and trigger a profound greenhouse warming. Some researchers have proposed that a bolide impact triggered or contributed to the eruptions. The evidence is ambiguous. What is clear is that Earth's geological record is a history of catastrophic resets, events that wiped out the dominant life forms and allowed new ones to radiate into the vacated ecological space. The Deccan Traps in India, a vast flood basalt province that was erupting at the time of the Chicxulub impact, may have been an important context for the end Cretaceous extinction, adding volcanic warming and ocean acidification on top of the impact-induced winter. There is evidence that the Chicxulub impact may have triggered or intensified the Deccan volcanism through seismic shockwaves propagating through the Earth, the kind of connection between seemingly unrelated geological events that speaks to the deep interconnectedness of Earth systems. The story of mass extinctions is never simple. It is always layered, always involving interactions between multiple stresses that compound each other in ways that a single cause in isolation might not. Earth's biosphere is more resilient than the extinction events might suggest. Life has survived every mass extinction in its history and diversified again. But the time scale of recovery is measured in millions of years, not thousands. And the world on the other side of an extinction event is fundamentally different from the world that preceded it. Space debris has become one of the most practically consequential issues in the near-term future of space activity. Since the launch of Sputnik in 1957, humanity has placed roughly 10,000 satellites in orbit, of which only about half are currently functioning. But the debris from these missions, spent rocket stages, defunct satellites, fragments from collisions and explosions, has accumulated to the point where the U.S. Space Surveillance Network currently tracks about 27,000 objects larger than 10 centimeters in low Earth orbit. Objects between 1 centimeter and 10 centimeters, too small to track individually but large enough to seriously damage or destroy a satellite, are estimated to number in the hundreds of thousands. Objects smaller than 1 centimeter number in the tens of millions. A 1 centimeter fragment in low Earth orbit is traveling at roughly 7.5 kilometers per second. At that speed, it carries the kinetic energy of a cannonball. A satellite struck by such a fragment is destroyed, and the collision generates hundreds of new fragments, each of which now poses a risk to other satellites. The scenario in which a collision generates fragments that cause more collisions, which generate more fragments, cascading into a self-sustaining chain reaction that fills low Earth orbit with debris too thick to safely navigate, is called the Kessler syndrome, named for NASA scientist Donald Kessler, who described it in 1978. Whether a true Kessler cascade is possible and at what debris density it would trigger is debated. But what is not debated is that the debris environment in low Earth orbit is deteriorating and that the planned mega-constellations of thousands of commercial satellites being placed by companies like SpaceX, OneWeb, and Amazon will dramatically increase the population of objects in these critical orbital zones. Active debris removal, using spacecraft to capture and deorbit old satellites and spent rocket stages, is considered essential for long-term sustainability, but no commercial-scale debris removal has yet been demonstrated. The window in which it remains feasible to clean up the orbital environment is not infinite. The International Astronomical Union's 2006 decision to reclassify Pluto as a dwarf planet, removing it from the list of planets and placing it into a new category, generated a public controversy that has not fully quieted in the nearly 2 decades since. The definition of a planet adopted at that General Assembly requires an object to orbit the Sun, to have sufficient mass for self-gravity to make it approximately spherical, and to have cleared the neighborhood around its orbit, meaning to have gravitationally dominated its orbital zone, either sweeping up other bodies or capturing them as moons or Trojan companions. Pluto fails the third criterion because it orbits within the Kuiper belt, sharing its orbital zone with thousands of other Kuiper belt objects. But the third criterion is itself scientifically awkward. It is scale-dependent, and by some formulations, Earth, if moved to Pluto's distance from the Sun, would also fail to clear its neighborhood. The debate continues in planetary science, and the classification, while officially adopted, remains contested by a significant faction of researchers who argue that geophysical definitions, based on what a body is, rather than where it is and what it shares its orbit with, are more scientifically meaningful. Eris, the dwarf planet that triggered the Pluto debate, is in some ways the more interesting object. Discovered in 2005 by Mike Brown, Chad Trujillo, and David Rabanowitz, Eris is about the same size as Pluto, possibly very slightly smaller, but about 27% more massive, making it the most massive known dwarf planet. Its orbit is highly elliptical, ranging from about 38 astronomical units to about 97 astronomical units from the Sun, currently near its farthest point. At that distance, Eris receives so little sunlight that its surface is frozen solid with nitrogen and methane ice. Its moon, Dysnomia, orbits it in about 16 days. Haumea, another Kuiper belt dwarf planet, is the most rapidly rotating large body in the solar system, completing one rotation in about 3 hours and 54 minutes, which has distorted it into a triaxial ellipsoid shape, flattened into an egg, rather than the spherical form that slower rotating bodies adopt. Haumea has 2 moons and, remarkably, a ring, the first ring discovered around a trans-Neptunian object, detected when Haumea occulted a background star in 2017, and the ring produced additional dips in brightness on either side of the main occultation. Makemake, a third Plutoid, has a small moon discovered by Hubble in 2016. The outer solar system, once thought to be a featureless cold wilderness, is a zoo of complex and varied worlds. The hypothetical Planet 9, if it exists, would be the most dramatic addition to the solar system census since the discovery of Neptune in 1846. Neptune's existence was predicted before its discovery, based on anomalies in the orbit of Uranus that turned out to be caused by an unknown gravitational body. The case for Planet 9 is similar in structure. A cluster of extreme trans-Neptunian objects, those with orbital periods exceeding 4,000 years and large orbital tilts, appear to be statistically aligned in a way that is difficult to explain by chance or by the combined gravitational effects of the known planets. The simplest explanation is a distant, unseen massive planet with the right orbit to shepherd these objects into their current configuration. The predicted Planet 9 would be roughly 5 to 10 Earth masses, at a distance of 400 to 800 astronomical units, between 13 and 25 times the distance from the Sun to Neptune. At that distance, even a planet of Earth's mass would be extraordinarily faint, and it would be moving so slowly against the background of stars that it might have already been photographed in existing sky surveys without being recognized as a planet. The search is ongoing, using wide-field infrared surveys that can detect cool, distant objects through the slight excess heat they emit. The Varro-Rubin Observatory, when it begins full survey operations, will cover the entire accessible sky to depths that should either reveal Planet 9 or effectively rule out its existence above a certain mass threshold. Every time we have pointed a new instrument at the sky, we have found something that was not in the inventory. Every time we have listened at a new wavelength or with a new sensitivity, the universe has shown us something that previously existed only in equations or speculation or silence. The radio sky, invisible to the naked eye, revealed pulsars and quasars and the cosmic microwave background. The X-ray sky revealed neutron star binaries and the hot gas-filling galaxy clusters. The infrared sky revealed the cool universe, dust-shrouded star-forming regions, brown dwarfs, the earliest galaxies. The gamma-ray sky revealed the most violent explosions in the universe. Gravitational waves revealed merging compact objects whose gravitational emissions carry physical information inaccessible to any form of light. Neutrino astronomy has begun, with the ice cube detector at the South Pole detecting high-energy neutrinos from extragalactic sources, including active galactic nuclei. The next instrument, whatever it is, will reveal something that is not in any current catalog. We live in a universe that is in the habit of surprising us. It is not a universe built to be understood by beings like us. It did not have us in mind when it arranged its physics. The fact that we can understand it at all is an accident of the same physics. The laws of nature that govern galaxy formation also govern the chemistry of neurons, the evolution of cognitive systems, the development of mathematics. We understand the universe with tools that the universe itself produced. That is either the most remarkable coincidence imaginable, or it is a deep truth about the relationship between physical law and the minds it generates. Either way, it is worth pausing on. The universe is old and we are new. The stars above you tonight have been burning since long before the first cell divided in the first ocean on this world. They do not know you are here. They will not notice when you are gone. They will continue turning hydrogen into helium, helium into heavier elements, building toward the supernovae that will scatter new generations of atoms into space, new clouds that will collapse into new solar systems, new worlds. The cycle of stellar birth and death has been running for 13 billion years and has a long future ahead of it. We have found ourselves, improbably, briefly, in the middle of it, watching, measuring, wondering. That will not last forever. But for now, it is what we do, and the sky, indifferent as it is, has given us everything we know.